Welcome to the second part of Module 6 of CE203 Fluid Mechanics 1. In this video, we'll be discussing Blasius boundary layer equations, drag and lift on immersed bodies, separation of boundary layer, and its control. In the coming videos, we'll be discussing the problems on Module 6. First topic is Blasius boundary layer equations. See, in some problems, the velocity profile will not be given. In those problems, we can use the equations given by Blasius. We have two sets of equations, one for laminar boundary layer and the other for turbulent boundary layer. So once you get the question, we need to identify whether it is laminar boundary layer or turbulent boundary layer. For identifying that, we can take the help of Reynolds number. Reynolds number Rex is equal to U into X by nu, where X is the distance from the leading edge, U is the free stream velocity, and nu is the kinematic viscosity of fluid. Here, when you use this value, instead of Rex, you can use Rel. You can take the entire length of the plate. So Rel is equal to U into L by nu, where L is the length of the plate. Here I have written Rel. Okay, so first find out what's the value of Reynolds number and then compare the value of Reynolds number. If Rel is less than 5 into 10 raised to 5, then it is laminar boundary layer. You can use these set of equations for delta, tau naught, CD and FT. If the Rel is between 5 into 10 raised to 5 and 10 raised to 7, then it is turbulent boundary layer. You can use these equations. Okay. Now, if Rel is between 10 raised to 7 and 10 raised to 8, then you can use this equation. All these equations are given by Blasius, and so we can easily solve the problems using these equations. Next topic is forces on immersed bodies. When a body is immersed in a flowing fluid, a force is exerted on the body. This total force is always perpendicular to the surface of the solid body. So here the total force acting on the body is Fr, and this Fr is perpendicular to the surface. We can resolve this Fr into its components. The component which is in the direction of motion of fluid is Ft. The component which is perpendicular to the direction of motion is Fl. Fd is known as the drag and Fl is known as the lift. So here components are Fl, which is perpendicular to the direction of fluid, and Fd is in the direction of fluid. Fd is drag and Fl is lift. Now we'll see the expression for drag and lift. Okay, so here you have a solid body, you have a small elemental area dA. PdA is the pressure force acting on the elemental area. Tau naught dA is the shear force acting on the elemental area, and the angles are also given in the figure. Okay, so when you derive the equation, we'll be getting PD, drag force PD is equal to integral P cos theta dA plus integral tau naught sin theta dA. Integral P cos theta dA is known as, this term is known as pressure drag or foam drag, and integral tau naught sin theta dA is known as the friction drag or skin drag. Similarly, you can derive the formula for lift force. Fl is equal to integral tau naught cos theta dA minus integral P sin theta dA. Okay. So this theta is the angle between the total force and the direction of motion. See here, this is the total force and this is the direction of motion. So this angle is theta, and it is same as this angle. This is also theta. Okay, so these are the expressions for drag and lift. Now we'll discuss more on pressure drag and friction drag. So we have seen that equation of Fd is equal to integral P cos theta dA plus integral tau naught sin theta dA. We have three different cases where we have, in some cases we have drag force as pressure drag alone. In some cases we have drag force as friction drag alone. In some other cases we have both the terms. Okay, so we'll see each case. First case is when theta is equal to 90 degree. So when theta is equal to 90 degree, the plate is parallel to the direction of motion. Suppose you have the direction of motion like this and the plate is like this. So in this case, plate is parallel to the direction of motion and theta is equal to 90 degree. When theta is equal to 90 degree, what is the value of cos theta? Cos theta is 0. That means this term will be cancelled off. So PD will be equal to integral tau naught sine theta dA ln. That means drag force is equal to friction drag. This term is not there. Okay. Now the second case, when theta is equal to 0 degree, that means the plate is perpendicular to the direction of the fluid. So this is the direction of motion of the fluid. The plate is like this, it is perpendicular. Okay, so in this case, theta is equal to 0 degree. That means this term is cancelled off. So only remaining term is the pressure drag. So in that case, drag is equal to pressure drag. Okay. Now we have the general case where the plate is inclined. Here you have the direction of motion and the plate is inclined just like this. Okay, theta has a value and both the terms will be present. So total drag is equal to friction drag plus pressure drag. I hope the difference between pressure drag and friction drag is clear to you. Next topic, expression for drag and lift. So these are the expressions. FD is equal to CD A rho U square by 2 and FL is equal to CL A rho U square by 2. CD and CL are the coefficients of drag and lift. A is area of the body, which is the projected area of the body perpendicular to the direction of flow, or it is the largest production of area of the immersed body. Okay, so A is basically area. So after finding FD and FL, you can take the resultant of FD and FL and find out the total force. So total force FR is equal to root of FD square plus FL square. We'll discuss problems based on this in the coming videos. Next topic is boundary layer separation. So in this figure you can see a boundary, a solid boundary, and this is the boundary layer. Okay, and velocity profiles are marked at point A, point B, point C, point D and point D. These are the velocity profiles. Okay, now we know that this surface offers a surface resistance to the particles which are very close to the solid body. So they are moving forward by doing work against this resistance. This resistance is offered by the solid body to the fluid particles. The fluid particles are moving forward by doing some work to resist this friction. Okay, so when they do work, their kinetic energy is reduced. They are losing their kinetic energy and going forward. So what happens is, consider this layer. Okay, this fluid layer, and when this fluid layer is moving forward, it is losing its kinetic energy. So this part of the fluid layer will be trying to recover its kinetic energy by taking some energy from the layer which is above that particular layer. Okay, so there is a transfer of energy or transfer of momentum from the above layer to the bottom layer. Okay, so they try to compensate the loss of energy and they move forward, but again the velocity is reducing, velocity goes on decreasing, and a stage comes where there is no difference between the energy of this layer and this layer. Okay, that means the velocities will be same. In such case, there is no difference in velocity, and that means velocity gradient becomes zero. So when such a situation occurs, the particle will not be able to stick on to the boundary of the solid body. So they will be going away from the boundary, and the boundary layer is separated from the boundary. Okay, so the point at which, see in this figure you can see that this point C is marked as the separation point. So at this point the boundary layer is at the verge of separation, and this point is known as separation point. Okay, hope boundary layer separation is clear to all of you. When the fluid is moving, the fluid is experiencing a resistance from the solid boundary, and this fluid particles is fighting against the resistance by losing its kinetic energy, and it is going forward, and it is taking some energy from the adjacent layer also, which has higher energy, and it is again moving, but still the velocity goes on decreasing. And then what happens, the velocities of the adjacent layers become same, and velocity gradient will be equal to 0 at this point. See here, du by dy at y is equal to 0 becomes 0. Okay, there is no difference in velocity between the layers. So when such a condition occurs, the particles are not able to stick onto the boundary, and it moves away. The boundary layer separates from the boundary, and all these points are written over here. The fluid layer adjacent to the solid body has to do work against the surface friction at the expense of their kinetic energy. So there is a loss of kinetic energy. This loss of kinetic energy is recovered from the nearest fluid layer having higher velocity. So there is an exchange of velocity. This exchange of velocity is known as momentum exchange process. Okay, so they are trying to adjust somehow, and this process goes on, and again still the velocity goes on decreasing, and a stage comes where there is no change in velocity. It is drawing energy from the adjacent layer, but still it is not able to move forward. The velocities of different layers becomes same, and there is no velocity gradient becomes 0 at the surface at this point. Okay, in such a case, the boundary layer is not able to stick onto the solid body, and it separates from the boundary. It moves away from the boundary. This phenomenon is known as boundary layer separation, and at the point at which it is about to separate, or it is at the verge of separation, is known as point of separation. At point of separation, velocity gradient will be equal to 0 at the surface. So du by dy at y is equal to 0 will be equal to 0. Okay, so this phenomenon is known as boundary layer separation. So this is the figure. Just have a look at this. It's point A, point B, point C, point D, and point D. These are the velocity profiles. Okay, so see here, there is enough gradient. There is difference in velocity between two layers. This is layer 1, this is layer 2. See, the velocities are different. But as you reach point C, there is a change in profile. If you consider this layer and this layer, there is no much difference between the velocities. Okay, and the boundary layer separates. And here you can see that velocity gradient is greater than 0 in this region, and beyond the point of separation, the velocity gradient is less than 0 at the surface. Okay, so you can relate this with respect to the pressure gradient also, dp by dx. Okay, so initially dp by dx, that is the pressure gradient, is less than 0, it is negative. So in such a case, there is an increase in the thickness of boundary layer. See, this is the edge of boundary layer, so there is an increase in the thickness of the boundary layer. That is a favorable condition. And at B, the pressure is minimum. And B, again, as we go beyond this point, what happens is dP by dx is positive. It is greater than 0. So in that case, the separation occurs. Okay. So we'll just discuss the pressure effect of pressure gradient also. From A to B, the velocity is increasing and the pressure is decreasing. That means we have a negative pressure gradient, and it is at the minimum, it is minimum at point B. Then in BCD, velocity decreases and pressure gradient increases. Initially it was negative, then now it is increasing. We have a positive pressure gradient. Okay, positive pressure gradient is not good for this boundary layer. If we have a positive boundary layer for a sufficient distance, positive pressure gradient for a sufficient distance, then the boundary layer will be separated. So it is not a good positive thing. Positive pressure gradient is not a positive thing for boundary layer. If we have a positive pressure gradient for an for a sufficient length, then the boundary layer will be separated. So what happens due to this positive pressure gradient and the surface resistance, the momentum of the fluid particles is reduced, and at one particular point the momentum is not able to overcome the surface resistance, or the velocity is reduced and the boundary layer separates. And we can see that after the point of separation there is reverse flow occurring. See, this is the velocity profile. The direction of velocity is changed. See, at E and D you have a reversal of direction of velocity. Okay, eddies are formed and there is separation of boundary layer. So this is the explanation of boundary layer separation considering the effect of pressure gradient. Okay. Now this formation of boundary layer is not a good thing, and in order to locate the separation point we have certain criteria. As I told you, if the pressure gradient at the surface is 0, then separation will occur. At that point separation will occur. So just to identify what is the condition of boundary layer, we have to find out the dou u by dou y value at y is equal to 0. If that value is negative, then the flow has already separated. If dou u by dou y at y is equal to 0, y is equal to 0 is 0, then the flow is on the verge of separation. It is the separation point. Okay. And if dou u by dou y at y is equal to 0 is positive, then the flow will not separate. It will remain attached to the surface. It has not separated. Okay. So by looking at the value of dou u by dou y at y is equal to 0, you can get an idea about the flow, whether it has been separated, or whether it is at the verge of separation, or whether it is already separated. All those things can be understood from this value. Okay. Now, as I told you, this boundary layer separation is not a positive thing. Loss of energy can occur due to boundary layer separation. So we need to prevent boundary layer separation. We'll discuss what are the different methods to prevent boundary layer separation. First one is rotating boundary in the direction of flow. So in this figure, you can see that here you have a solid body and this is the direction of flow. So in order to avoid boundary layer separation, we are rotating the solid body itself in the direction of flows. So you can see the arrow. So the body is rotated in this direction, in the direction of motion. So this will eliminate the boundary layer separation. That is first method. Then supplying additional energy from a blower. See, in this case, we have a blower over here and some energy is supplied from this blower. Okay, so that here if there is any loss of energy, the fluid particles can take energy from here. So this is second method. Then third one is providing a bypass in the slotted wing. Yeah, here we can give some slots. This is the cross section of this airfoil. It is the cross section of the wing of an aircraft. So there, if you are giving slots like this, more energy, more velocity will be available over here, and we can prevent boundary layer separation. Then there is also suction of slow moving fluid by a suction slot. So we have seen that the velocity is reduced. So if there is any very slow moving fluid element, those fluid elements can be sucked in through the suction slot. Okay. So this method can also prevent boundary layer separation. So these are the different methods you can explain with the help of the figure. So that's all for this video. In the coming videos, we'll be discussing the problems. We have identified 6 types of problems from module 6. So these are a few types. Okay, hope to see you in the next video. Thank you.